Perfect. Hi everyone. Welcome to another installment of the IGS Global Seminar Series. This week we are shifting to a new topic, one that we haven't touched upon before. This week we have Dr. Joshua Culpepper from York University here in Canada. Josh is a postdoc there who specializes in lake ice, and so he's agreed to give us a great presentation on lake ice and its changes as a result of climate change. As per usual, please hold your questions until the end of the talk. You can either drop them in the chat bar or just hold on and we'll call on people who raise their hand at the end of the talk. But without further ado, I will pass it over to Josh.
All right. Thank you so much. You can hear me okay? Everything's good? Great. Yeah, thank you so much for the invite. I'm happy to be talking to a not necessarily limnologically focused group for the first time in a while. Um, yeah, like I was introduced, I'm Josh Culpepper. I'm a postdoc in the Department of Biology. I did my PhD on hydrology, but really a surface water focus, and much of my work was on mountain systems and lakes and mountain systems, and those freeze quite a bit. So I got into more ice related work. So here you can see an image of one of my colleagues as we're taking some samples, and you'll see that this is a good example of what we call black ice. You might also hear it called clear ice or congelation ice. And then there's also, of course, there's white ice. I mean, I'm oversimplifying a little bit, but we're going to be talking about lake ice quality and how that might be changing or varying in a warming world. There we go. So when we usually talk about lake ice, excuse me, and in general, when we think about winter limnology, we're often thinking about the phenological processes. So the formation and the breakup, and those combined making the duration. So a lot of the work on lake ice has to do with these processes and how they respond and how they're a good barometer of climate change because ice responds really sensitively to climate change. I'm sure everybody here knows that, but lake ice responds quite rapidly. So you can see here is actually this is a projection of ice formation on the left here, ice breakup in the middle, and ice duration on the right. And the way this is set up, these colors relate to the anomalous behavior of a 4-degree warmer world compared to a historical context of 1850 to 1880. And you can see that in this 4-degree warmer world, we anticipate later ice formation, in some coastal regions in North America and in Europe, um, a much delayed ice formation of up to 20 days or more, a breakup in the Arctic and in Europe, in the lower latitudes in North America. We can see a distinct, much earlier breakup of 20 or more days. And combined, we see in some areas of the world, I'll let you kind of look at the map, but in those same sorts of regions, an overall loss of duration of ice cover of more than 25 days. Um, there are, based on the approach, there are some different numbers, but overall, we do see losses of up to a month. In addition to kind of these projections, the global records that are kept, or at least the most comprehensive global records, show that ice loss is also accelerating when comparing the most recent 25 years compared to the last century. And what does that mean? In addition to lake ice forming later and breaking up earlier, we also know that lake ice is getting thinner. And we also know that lots of people use lake ice for recreation, for transportation. There's, basically innumerable uses. Lots of people are using lake ice throughout the season to fish and to skate, etc. And on this plot on the left-hand side, we can see the number of drownings per million people. That's on the y-axis. And on the x-axis, we have the average, basically winter temperature, December to March temperature in degrees Celsius. And you can see this non-linear relationship as you approach zero, you get more and more drownings. And some of that has to do with um, access to ice, people who are constantly around ice. Some of it has to do with local regulations, whether or not people have more stringent regulations on letting people onto ice, or more lax regulations. But a lot of it has to do with the strength of ice as we approach 0 degrees Celsius on lakes. You have this combination of the ice is either forming or melting, and when you have these warmer winters, you have thinner ice, and you're more likely to lead to these kind of dangerous accidents. In addition to kind of the ice phenology and the safety question, to the safety, we have to add the quality question, because white ice, as just a general rule of thumb, is about half the strength of black ice. This has to do with the kind of random crystal orientation. You have these small snow crystals that are like kind of refrozen slush, or where the snow has pushed the ice sheet below the hydrostatic surface. You get a lot of flooding into the snow pore space. That freezes. You get all these randomly oriented and small crystals. Whereas congelation ice or black ice, it forms much larger crystals that are all in sort of the same direction. It gives it a lot more strength. Now, when it gets really, really cold, there isn't too much of a difference, it seems, between white ice and black ice, but especially near these 0 degree temperatures, white ice has been measured to be about half the strength of black ice. We also can see that from this what's called the Ice Blitz project. Basically, it was like an attempt at a global perspective of ice quality, because ice quality is quite lacking. So they went out over the course of a winter in 2020, which was quite warm, for large parts of the northern hemisphere, and they found that you could have almost a complete white ice sheet as early as February. So it's not unrealistic to think that you might have in a much warmer winters to have almost completely white ice sheets. Some of that has to do with the lack of growth of black ice in these warmer winters, and just the ice that's forming is from this refloat frozen slush, and also kind of melt freeze cycles that add a lot of bubbles, for example, into the ice sheet, and you get these white ice layers. So we started thinking a lot about this, and we tried to think about it from a few different perspectives. One is kind of just an overall, what can current observations tell us about the contemporary and future ice quality conditions? Second, we were also thinking about how that timing of safe ice availability might change in warming climates. And lastly, we wanted to actually go in and see some of get some actual data on how winter hydroclimate variability can impact ice quality and under ice water quality conditions. So what you might see in a winter to winter basis, a warm winter to a cold winter, we've been experiencing a lot of that in my part of Canada. So we'll kind of go over all of this, but first we'll start with that kind of larger review. So here we're looking at just two conceptual models, one being kind of a historical condition on the top with more black ice and less white ice, and then on the bottom with less black ice and a bit more white ice, some of that warmer conditions that I've been mentioning. And we wanted to think about some of the major implications of these changes. So, for example, black ice allows a much higher transmission of light from incident radiation into the water surface and into the water column. And then with that, you may get additional kind of circulation, which can be important for nutrients and phytoplankton. And also, when you have more light, more autotrophic production, then you can also get kind of a larger, a more diverse community of phytoplankton, zooplankton, and that's of course going to go up to things like fish. So a healthier kind of trophic state. And then when you have more white ice, you have less light transmission. You're going to get less circulation of those nutrients, for example. And then also you have more specialists, more mixotrophs, things that are going to be able to not just photosynthesize, but also consume material. So you get kind of a more reduced, less diverse community. And that's going to have some implications, particularly for these cold water fish that might be using the winter period to grow. In addition to that, you can see the kind of truck in the top section and the kind of concerned person with the breaking ice in the lower section. Um, and that's just to represent kind of that strength difference that we were noting. In addition to kind of thicker overall ice when it's colder, also you have that added complexity of white ice, which can be weaker than black ice in certain situations. Okay, so we went and found the records that we could, but it turns out that ice quality is pretty scarce, particularly when you want to look for something like a long-term record. The best records we could find came that top time series is Lake Vendyursko in Russia. So on the y-axis, you have ice thickness just in centimeters, and then you have a time series. And what you can see is these pink triangles are showing the overall ice thickness. The black circles are showing the black ice thickness, and the kind of bluish gray boxes are showing the white ice thickness. And I have those solid and dashed lines to show that there was a significant trend of overall declining ice thickness. That's the total ice column. There was also a significant trend in black ice thickness declining, but no trend in white ice thickness. Taken together, we can sort of infer that there's an increase in the proportion or the percentage of the total ice column that is white. If the overall ice column is declining, the black ice column is declining, and we have white ice, we were thinking, okay, well, maybe this means that it's kind of what we were anticipating, what people saw on the Ice Blitz project, an increase in the proportion of white ice, even if white ice itself isn't increasing. Then we looked at Finnish lakes, which the Finnish Meteorological Institute actually has a really nice, kind of robust ice quality monitoring, ice thickness and ice quality monitoring system. And uh, we looked at lakes that had more than 30 years of data, and we found that both the total ice and mean ice thicknesses were showing significant a significant decline. The trend is what we're seeing on the y-axis. And the white ice and both the maximum and the mean white ice thickness were increasing, where there were no significant trends in black ice. So again, the total ice thickness declining and the white ice thickness increasing. So an overall proportion of an increase in white ice. And then we looked at this using the community Earth system model to look at projections of ice thickness into the future. And what we see is on the left-hand side here, 1 degree Celsius of warming, and on the right side, 2 degrees Celsius of warming. And we're looking at the kind of anomalous behavior again, the 1 degree and 2 degrees Celsius warming compared to a historical average. Um, and what we see is overall, almost completely across the board, we see a decline in overall ice thickness. We can't assess from this model the increase or decrease in white ice or black ice, but we see an overall decline in ice thickness totally, taken together with some of our assessments of potentially increasing white ice, though that is geographically constrained. Um, but taken together, we can anticipate that, especially in these Arctic regions, even in lower latitude regions in, for example, Eastern Canada as well, um, more dangerous kind of ice conditions, that combination of a thinner ice cover and potentially more white ice. Shifting gears to think more about the biological implications, what I pointed to earlier, that change in albedo, the fact that black ice allows a lot more light to enter into the water column. Um, we also want to know more about what's happening in the winter, previously kind of assumed to be a sort of quiescent period in lakes where they're just sort of most things are pretty dormant. We now know that there's actually quite a bit of activity, and we're starting to learn more and more about that. And here's some data from a paper that came out in 2023 looking at chlorophyll A They also looked at community composition and biomass, but I'll just be just showing you kind of the chlorophyll A assessment here that we reported on in that review. And here we have the chlorophyll A on the y-axis, and then the box and whisker plots represent different years. And we had a snow-covered year, so basically just a control year. How would this lake normally behave? We have a snow removed year. So the experiment was to basically remove snow from this lake surface, see what happened to the chemical and biological signals. But they weren't able to get out until later in the season. It was a milder season. It took longer for the ice to build up because they actually had to go out and drive basically a plow on that lake, so it had to be sufficient to support that. So they got out late, and there was a much higher proportion of white ice that had already built up by the time they got out there. And then in the snow removed year on the far right, they were able to get out a bit earlier. It was a colder year, and most of that ice sheet remained black ice. And so they had quite a bit more light in that year. And in the surface chlorophyll A measurements, it increased by up to 500% in the snow removed years with a very high peak chlorophyll A. That is really due partially to the trophic state of the system rather than just the light availability. Again, this is just one lake, so I don't want to cast too broad of a net, but the idea here is primarily that when you have more light, you can get more chlorophyll A. They also showed that there was a more diverse community of phytoplankton. So that's kind of that larger review sense, kind of what have we gleaned from what's available and what could potentially go on in the future, considering projections. And now we'll think a little bit more about that projections into the future, but looking at the timing of when ice is safe. So when lake ice is there, but sufficient for people to walk on, or at least kind of use in a safe manner. So this unsafe period occurs when ice is available, but it's not sufficiently thick to walk on, right? So if you've ever stepped out on a frozen lake and your first step, the ice starts to kind of splinter underneath you, you know that feeling, that kind of drop in your stomach, and you stay off the ice, right? Well, in general, most municipalities say that they want at least 10 centimeters of black ice, the kind of stronger black ice for people. And then the rule of thumb is to kind of double it if you see a percentage of a higher percentage of white ice. Though to get to that, you may need to kind of drill into the ice surface. So when you see white ice, so just be particularly cautious. So we were thinking about that 10 centimeter threshold. And this conceptual model is really just to illustrate a general winter ice cover period. So the ice forms, increases in thickness. When it crosses that 10 centimeter threshold, it becomes safe to use. You get your maximum thickness, then it melts. And then you get another period toward the end of the season where it crosses below that 10 centimeter threshold, and the ice becomes unsafe again. And so that's just the general idea. So what happens if it gets warmer, if the ice is thinner, or if the ice quality changes? What we wanted to look at was, say, for example, in a future projection, this orange line, the ice is thinner, and it also takes longer to reach that 10 centimeter threshold. So the ice is, we know shifting from our earlier discussion about phenology. But when the ice is available and when it finally crosses that 10 centimeter threshold, and then when you combine that with the complication of the ice quality, then what happens to this unsafe period? So we're kind of thinking of this as like a shoulder season. We're kind of in between the open water period and the usable ice period. And so here, maybe I should have shown this earlier, but here's some examples of black ice and white ice. So on the left side here, this is actually taken from two different lakes. So on the left side is a lake in southern Ontario, about an hour north of Toronto. You'll see some more of that later from our other work in that area. And this is black ice. It's entirely black ice. It's about 15 centimeters of black ice, I believe, or between 10 and 15. This was kind of a warmer year and had thinner ice cover. You can see that kind of from the side, it sort of looks a bit white. That really is just an effect of us removing the ice core from the ice sheet. We have to use a big saw and it kind of just gouges outside. So you're seeing that kind of reflection, but you can see just behind it, you can see that it's quite clear. However, the two middle images are taken from a different lake about another hour north of this lake, and you can see that there's almost I think this one is exactly a 50% white ice and 50% black ice. You can see some bubbling in the black ice layer, but that's probably just an effect of how rapidly the ice was forming. And then on the far right, you see an almost completely white ice column. There's a little bit of black ice on the bottom, I think 2 or 3 centimeters, but most of that ice column was white ice. So yeah, not an outlandish scenario to have a completely white ice column. And from some of that ice splits project, we saw that that could happen as early as February in that year. So we use the community or system model again to look both at the past and future conditions of these systems. This is a 100 N member model. So basically we're using the mean of those 100 N members, and we're calculating lake ice thickness. So that's kind of a deficit of this analysis, that we can't really tell the difference between white or black ice increasing or decreasing. We're using the thickness thresholds to indicate the safety, and kind of assuming, if we had 100% white ice or if we had 100% black ice, and we calculated the uh, uh, capacity based on those measurements. So here I'm just showing you the 4 Celsius warmer world, where on the left hand side we have the ice formation period. On the right hand side we have the ice melt period. And on the top, we have a completely black ice scenario. In the middle, the 50% white ice scenario. And on the bottom, excuse me, the completely white ice scenario. And the colored tiles are the anomalous behavior of this 4 Celsius warmer world versus a historical condition, which is an average of 1850 to 1880. And in that 100% white ice condition, that period, unsafe ice period, when ice is present but not sufficiently thick, increases by 29 days. So not only are we getting a period of later ice formation in this warmer world and earlier ice breakup, we're also getting an extended period when the ice is available but unsafe. And we can see that portions of, for example, Eastern Canada, there's a large population over here, and areas in like Northern Europe have some of the highest losses in terms of a safe ice period. Now, taking that data from kind of a geospatial context into just a distribution, we can see that the effect of temperature is smaller than the effect of the changes of ice quality. So when you look from 1 degree Celsius warming to 4 degrees Celsius warming, on the left-hand side is the formation period, that orange color, and then the red color is the melt period. And we're seeing kind of the entire northern hemisphere conditions. We can see that it expands. You get this more rightly skewed distribution. However, when you move into the white ice, the higher white ice scenario, you get much more of these much longer these transition periods, this anomaly. So the ice conditions, the ice quality seems to have a bigger impact than just the warming on its own, though the warming does have a significant impact. Okay, now moving from kind of these large scale like modeling approaches, we also wanted to actually go out and take some samples, see what we could find, see how different the ice quality could be on a year-to-year basis and what that might mean to the conditions under the ice. So here we have a map. These are the lakes that I was mentioning before. This is Lake Simcoe, and we sample Kempenfelt Bay on Lake Simcoe. That's an embayment on the west side of the lake. It's the deepest area in the lake, and that the shape kind of really acts like sort of a runway, like a funnel for the wind. So it can blow a lot of the snow that might normally stick onto the lake. It can blow it off, and you can continue to get some of that black ice growth rather than just it kind of sticking and turning into white ice as it kind of melts or gets inundated. And then about an hour north of that is an area called Paint Lake. This is a much smaller system. but we sampled two parts of that lake. We have the deeper, larger basin, and then we have the shallower embayment. Not sure if you can see my mouse there, but there's a shallower outlet that we sampled. That's about 5 meters, and the area we sampled here is about 17 meters. So basically, just two basins of that smaller system. And we can see the examples of the ice. And we just so happened to be sampling in a very warm year, which is 2024. That was top row of pictures. And then 2025 was a much colder year compared to 2024. And you see much thicker ice and a much more kind of complex white ice layering, where you have some of this ice that's really superimposed onto the black ice, as well as layers of slush and other white ice layers that are sometimes fused and sometimes not fused to the main core. So you see a lot more kind of complexity compared to this warmer year. You can also see that there's a lot more black ice total in the even in the system that had like more white ice um, in the colder year. So a lot of differences. And so here is kind of just a look at an anomaly based on the temperature and the precipitation. So temperature is the A and B panel, and snow is the C and D panel. And in 2024, we saw much warmer temperatures compared to the 23-year average. I chose that period of time because it's the longest continuous record of meteorological data that I could find near the lakes. Um, and then in 20, or sorry, so I should also say, and then there was less snow, especially compared to 2025, but also compared to the 23-year average. Um, and then the temperatures were close to that average, but there was a lot more snow, nothing like particularly record breaking, but much more snow, especially compared to 2024, which was much drier. And here is a look at the data of the ice cores that we were able to take. Um, in 2024, we weren't able to go out as much, particularly on Kempenfelt Bay. Like I was saying, the ice kind of hovered around 10 to 15 centimeters, so it wasn't always safe. There were a few times we were asked to stay off the ice. So that's the kind of gap in our records there, and why our records are a bit more truncated. And then in 2025, we can see the much thicker ice column. Um, as well as more snow in that 2025 period. And then we'll also look at the proportion of ice that was black ice or white ice. You can see in 2024 in Kempenfelt Bay, that top area. And I should mention, I kind of just ordered these from like deepest to shallowest. So the deepest being Kempenfelt Bay, the deep site in Paint Lake, and then the shallow site in Paint Lake on the bottom. And here we're looking at the percent that was black and white. So in 2024, only black ice appeared on Kempenfelt Bay, but in 2025, a little bit of white ice formed, though still predominantly black ice. In Paint Lake and the deep site, primarily white ice in 2024 from the start throughout. It didn't change very much. But in the cold year in 2025, we started out with primarily black ice, and then that slowly shifted as it got much thicker and thicker white ice. Um, the black ice didn't started to melt toward the end, but this is primarily just the white ice taking over. If you recall those images of the white ice sheet that I showed you. And in Paint Lake, there wasn't actually a significant difference between the 2 years. This may have to do with earlier forming of the ice sheet in Paint Lake, but there was overall thicker ice, but the proportions were not significantly different from one. Looking at PAR, so for photosynthetically active radiation, that band of the wavelength that phytoplankton will use to photosynthesize. We were interested in that. So we took measurements of incident radiation above the snow and above the ice. And then we took measurements underneath the ice, right at the ice water interface. We did that both before removing the snow. So we tried to make sure not to disturb the snow. And we covered up the hole with like an opaque sheet to try to mitigate any kind of like light interference from the hole that we had to drill to put the instrument in. And then we took another sample at the ice water interface when we removed the snow, if there was snow present. So the top, we're seeing snow and par, and this is not just the raw par values, this is the percent of ice transmitted through the ice sheet. So you can see that anything above, say, 3 centimeters reduced the average par transmission to around 5% or less. And then once we removed the snow, you got a higher proportion of par entering into the water column, but we still do have a similar shape, where as you get a higher fraction of white ice, you get um, diminished light transmission. Now, we also took like a high frequency depth profiles with a sonde. We looked at temperature, dissolved oxygen, and chlorophyll A. So here we're looking at the temperature for, again, it's in the same order, Kemptville Bay at the top, Paint Lake, the deeper site in the middle, and Paint Lake, the shallow site in the bottom. And what you can see is a really well mixed layer throughout the water column. Note the different depths here on the y-axis. Um, a much more well-mixed water column in 2024 than in 2025. Kemptville Bay, it just has very cold water temperatures. However, we do see warmer water temperatures, as you might expect, sort of that inverse stratification underneath the ice, where the surface is closer to 0 degrees and you warm up as you move down, where it increases in density. You can see that better illustrated in the Paint Lake Deep site, where again, it was more well mixed in 2024, but in 2025, you can see that cooler layer just below the ice water interface, and then that warms up to nearly 4 degrees as you move down to the deepest part of the water column. 20 in the Paint Lake Shallow. It looks fairly similar here. We were able to go out later into the season, so we're starting to see that mixing occur. However, some of that mixing didn't go all the way to the bottom. Part of that has to do with um, road salt inputs. So a colleague of mine is working on that paper. We saw a lot of total dissolved solutes in the bottom layers, and we saw that most of those are sodium and chloride. So this is likely inputs of road salts from the nearby highway is affecting this shallow outlet basin. And you can see that there are temperatures above 4 degrees Celsius deeper in the water column, which those temperatures should be lighter, less dense, and they should move above that 4 degrees. But it doesn't do that, and this is likely due to those solutes. Okay, and here's oxygen. It's sort of a similar story to temperature. We see a really well mixed layer. We see higher oxygen levels um, in the warmer year than in the colder year. Ice forming earlier and then impacting that the decay of or the consumption of oxygen, particularly in these shallow regions. We can see that area grow. Here we have it at 8 milligrams per liter, kind of as our middle threshold. That had to do with Kemptville Bay's desire for higher dissolved oxygen concentrations, um, owing to like their population of cold fish and how important the sporting industry is in Kemptville Bay. So we marked it at 8 milligrams per liter. So if you were to shift it to say like a hypoxic condition, like 4 or 2 milligrams per liter, a lower oxygen threshold, this would look different, but you'd see a similar pattern. And you can really see that low dissolved oxygen concentration area grow before that mixing starts to occur that we saw with the temperature. And then finally, we have the chlorophyll A, and you can see the green is the higher chlorophyll A concentrations. Here, our threshold was kind of 2 milligrams per liter because these are quite clear systems. So kind of a lower trophic status, more oligotrophic, quasi-mesotrophic systems. And so in these areas where there's more than 2 milligrams per liter, you're starting to see really where the higher concentration of chlorophyll A activity is. With all of that light available in 2024 and that in the year with less snow, um, you could see that there is, I mean, minimal chlorophyll. Again, it's a very clear system, but you can see a higher concentration around 15 meters because there was a lot of light penetration. With the higher concentrations of white ice, or a higher proportion of white ice in Paint Lake in both basins, we see a higher concentration near the surface, but you can see that it's more expansive in that year with less snow, more and higher light availability. You can see that in both basins of Paint Lake. Here we see that kind of concentration really only near the top in the surface, and then it kind of goes away a bit owing to the really high depths of snow. And then it comes back as that snow began to melt. We see that happening again in the Paint Lake shallow system, but with significantly less, lower concentrations of chlorophyll in the cold year compared to the warm year. So just to kind of recap, um, lake ice quality is important, but really it's an understudied component of the cryosphere, particularly in freshwater systems where we do get these dynamics. I'll mention, of course, that there's going to be a lot of heterogeneous ice quality as you look around, like in different areas, due to like various things, like local landscape factors. For example, the differences between Paint Lake and Lake Simcoe are potentially due to the impact of wind, wind having a higher impact on Kempenfelt Bay, able to move away more snow and do a continued growth of black ice, whereas you have a more sheltered forested system on Paint Lake, where you can get a higher proportion of white ice. So these are things that are interesting and important to sample. And we kind of encourage people to take more samples if you go out on frozen lakes at all. Um, then, of course, we talked about kind of a larger modeling study looking at the impact of ice quality on safety. And we saw that a potential increase of up to 29 days of limited ice use when ice may not be safe as a Northern Hemisphere average, especially impacted our Eastern Canada and Northern Europe. Um, and that the ice quality had a larger impact than the increase in temperature. And then finally, warmer winters were leading to cooler water temperatures, higher dissolved oxygen, and higher chlorophyll A concentrations due to a combination of likely later ice formation, allowing a greater mixing for temperature and dissolved oxygen, and then a higher amount of light, permitting higher concentrations of chlorophyll A in the warm year. With that, I just want to thank everyone for listening. I want to thank Lake Simcoe Science and Arctic Net for funding and supporting this research, as well as members of my lab, the Sharma Lab, for their assistance with sampling and listening to all these ideas. So with that, I'm happy to take any questions.
Perfect. Thanks, Josh. That was a great talk. We'll open it up for any questions. So if you have a question, please raise your hand or drop it in the chat. Maybe I'll get us started. So the difference between black ice and white ice on a lake, is it purely just temperature driven, so the rate of growth, or what
Yeah,
other variables go
yeah,
into it?
yeah, I can definitely explain that farther. So it's really two completely different growth types. So black ice or congelation ice, named so because it kind of congeals into the surface. So it's that initial layer of ice you see form, and then it grows in parallel to the direction of heat loss. And so it grows these kind of much bigger crystal structures. They're all kind of similarly oriented, and we're kind of looking down the axis of the crystal, and that's why it's so kind of black, or why it looks black, right? We're seeing all the light be absorbed by the
Yeah.
water. You pull it out and looks clear, of course. And then the layer of ice that builds on top of that initial layer is the white ice layer. So that can form from a few different things. Like you said, there is a temperature component where if you as you get ice on the surface that's like melting and then refreezing, you can get a lot of bubbles that can look more white ice. But then also there's the component of snow, so precipitation. When you get that snow sitting on top, not only is the snow going to go through melt and freeze cycles, or if you get things like rain on snow events, that's going to fill that pore space with water, you get that slush, and that could also freeze. You can also have the snow, it's heavy enough that it's going to push the ice below the hydrostatic surface, and then water can come in through cracks or around the edges, fill in that pore space, and then refreeze. That's where we get all those complex layerings of white ice that I showed a small segment of, but I have many pictures showing lots of different kind of types of configurations. So yeah, you get that initial black ice layer forming into the water surface, and then the ice that's superimposed onto that black ice. It can fuse with it. It can kind of stay sort of slightly not quite fused with it, and it has to do with just this, for example, the snow working as an insulating layer and not really allowing as much growth of that white ice. The insulative layer of snow can also halt the black ice growth as well.
Hmm. Okay, interesting. So my background is in sea ice. So when we drill a sea ice core, we have a top layer of frazzle ice that forms right when the sea ice starts to form, and then like the lake ice, we form this long layer of congelation ice, and that grows down. But in lake ice, this white ice is sort of ice that is, subsequently added to the upper surface of the ice pack.
Yeah, and in fresh waters, you really get frizzle ice more in moving waters. So you get it more in rivers,
Okay, where you get those
where
crystals
yeah,
accumulating.
yeah, when you start to get those crystals and they're sufficient enough and they're not being pushed around, that they can start kind of floating downstream, and then you get those spins, and then you get things like pancake ice. But yeah, you don't get that as much in lakes because they can be much calmer than the
Yeah.
moving water and then the big tidal forces you get in the ocean. So yeah, you can get that calm layer of like initial ice, and then the other ice, it forms perpendicular to that initial layer, but you get those bigger crystals, and so you can get that
Yeah.
black ice, which you don't really get in the ocean, is my understanding.
Yeah. Interesting. Anyone else? Stephen. Yeah.
Um, yeah, this is very interesting. Thanks for offering this talk. Yeah, my question is about you showed a sketch of the time series through the winter of ice thickness and showing it starts out growing slowly and then gets more rapid increase in thickness. But then in the springtime melting, it's melting rapidly, but then the melt rate slows down and you have a slower melt rate. And I almost like a mirror image. Now I know it's just a sketch, but how realistic is that? I would have expected that once it starts melting, it kind of goes really fast. That
Yeah, you are right. Yeah, that sketch, we kind of thought about how should we convey that, because you can get quite a rapid drop off once the ice sufficiently melts, especially if you have, for example, a bigger system where you can get more of that kind of wind impact. Once it starts to break, it all kind of pushes to a side, and it's gone. So it's really going to be it would depend on a lot of different variables. And just for the conceptual model, we were just thinking, okay, there's a period when there's ice and it's not sufficiently thick on both ends. But yeah, on when it's melting, yeah, I would expect it to be a bit faster. So maybe
okay.
modeling it on some actual data would be good, but often you don't have any data when the ice is breaking up, because no one's out there to measure it.
Interesting. Andrew, we'll call on Andrew, even though he is wearing a glaciology hoodie to a lake ice presentation today.
Thanks, Dave. Thanks, Josh. Great talk. The question about the community Earth system model. So my understanding is the resolution of that model is not sufficient to actually resolve lakes. So how are you actually estimating lake ice growth from the community Earth system model?
Yeah, so there is a lake ice component. There's a lake ice model within it, and you have 1 degree by 1 degree approximately uh, uh, grids. And so, yeah, it like when you go and look at like an individual lake, it will probably look really different from the model, because you have a really large space, and it's just accounting for the total surface area in that grid, and then it's using a lake that is the average depth of the lakes in that grid. So you're going to get really probably different um, behavior, actual behavior, if you were to actually go out and kind of look at it. Because we have, they've used that model for both ice phenology and ice thickness models or studies, and that is one of the main criticisms of it, right? That it's kind of overgeneralizing the behavior of those systems. So I agree, but it was one of the best ways to kind of look at the in northern hemisphere as a whole. So yeah, you're looking at an average behavior of lakes in that grid. So going out and seeing a larger lake or a smaller lake, it's going to have really different behavior. And there's a snow compression component to that model, but um, it's you're going to have as I showed in that from lakes that are really close together. So those would be almost be in the same grid cell. You have really different behavior in the white ice and black ice components, and also the ice thickness components. Um, and that has to do partially to differences in snow, differences in wind. So yeah, it's definitely not going to be a perfect model by any stretch of the imagination, but it was a way to look at kind of the entire northern hemisphere at once.
Yeah, yeah, thanks. That's helpful. So it starts out with some sort of idealized, say, temperature profile over, let's say, a 30-meter deep lake or something like that,
Yeah,
and then just
e-
runs it based on atmospheric forcing.
exactly, exactly.
Okay, thanks.
Anyone else? I had a quick question about you presented the sort of long-term observations from a lake in Russia and a lake in Finland, or maybe
Yeah,
several lakes in Finland.
yeah, yeah.
Are there any others? Like, does Canada have any um, long records of lake ice thickness or freeze up, or Alaska or places like that?
There's some with thickness. So you do, when you look into ice thickness, you can get a larger population of data. But when you want the ice quality component, that's when you start to lose lakes because a lot of people just go out with they drill a hole with an auger, they get a measuring stick in the hole, and they measure the total ice thickness. And that's obviously better than nothing. And those measurements are being used to do things like try to get at remote sensing components of lake ice thickness. And so there's cool things happening with like synthetic aperture radar on ice thickness. And there's other I think someone at ArcticNet was talking about yeah, kind of using I think this was for sea ice though, but using basically a skidoo and running a sonar behind it basically, and getting a bunch of ice thickness measurements and using that with satellites as well. So there's a lot of advancement that can go into the thickness component, but quality you really have to go out and just measure it, and that's one of the problems. So for example, the Finnish Meteorological Institute, they have a really kind of robust ice quality measurement system, like different ways of measuring the ice quality. And I had to work with a hydrologist there to kind of not only because I don't speak Finnish, but also to kind of get a hold of all of the to understand the metadata a bit better. There are some lakes in Sweden that have published data now, but at the time of working on that, we did not find those lakes. But there is a paper, Vikström et al. 2022, I want, or maybe yeah, 2022, 2023. And he's a current colleague of mine actually. But they did work on ice quality in Sweden, so they found a lot of Swedish lakes. But when you get to ice quality, you lose a lot of lakes. So that's why we're kind of trying to start this longer term, but it's only two lakes, right? So it's the constant battle.
Interesting. Maybe just quickly before we go to Alan, when you do take an ice sample, is it very clear? Like you can measure in the field, oh, X centimeters of black ice and Y centimeters of white ice. It's a very clear delineation between the two ice types.
Yeah, good question. So it can be really easy. Sometimes when the core is just fully fused, and you cut it out and you pull it out, there's usually a really clear line between the white ice and the black ice. Maybe like a millimeter here or there where it's kind of like where you see the fusion. But oops, that can be really easy. But some of the pictures I showed where it's like chunks with like slush in the middle, those often come out in chunks.
Okay.
And the water that's in those layers is buoying the ice a little bit. So when you pull them out, you lose some of the thickness. So we try to measure every component of it, and like we basically draw a little schematic and say like, okay, black ice, that's always quite easy to measure. And
Mhm.
then you have like some white ice that maybe is the superimposed ice, but then there's like a slush layer, and then a white ice layer, and then a slush layer, and then a white ice layer. So we try to measure all those as best we can, and then we also take a measurement of the auger hole, and that will be like the total ice
Mhm.
thickness that we give it because that water layer kind of pushes on the ice sheet a little bit. And if you're ever out on a lake that has some white ice, sometimes you'll feel that like as you're walking, if the layer hasn't frozen completely, you might break through into like a slush layer. And then you're kind of standing on the black ice or white ice layer, but then there's a slush layer and then there's an ice layer above it. So it can be a little hard to measure. Which is actually in the Finnish Meteorological Institute. They have something called they called it like stick ice, I think was the direct translation. And I had to ask a clarifying question, and they were like, "Oh yeah, this wouldn't make any sense." So basically, they drill a pole with measurements into the black ice when it's there, when it's sufficient enough to kind of drill it in, and then they can measure the white ice growth on top of the pole, which is a kind of an ingenious way of measuring
Oh,
it. And then they do all their other measurements in addition to it, but then they have a metric of like this is pushed into the black ice, so we're measuring, the white ice that's formed above it.
okay. Interesting. Alan.
Yeah. So I was curious about, you're talking about ice quality. And I'm coming at this from a recreational point of view as well. People are looking for like smooth ice to go skating on, wild ice that's both safe and smooth. And I'm wondering, is that like something that is modelable in a real sort of way? And do you work with like citizen scientists or recreational skaters to collect data at all as well?
That's a great point, actually. I did an interview with a journalist, and they were also interviewing a wild ice skater. So they ended up interviewing me because the wild ice skater was like talking about types of ice. So they asked me for some clarifying like points from a more scientific point of view. And this wild ice skater, they go out into the like mountains like as early as possible. So this is like in like the Rockies and stuff. But they go all over the world. They've been to like Tibet and stuff, and they'll skate when the ice is what did they say? I think they said 2 inches thick. But they listen. They have a couple different methods of doing it. But one of them is like throwing a rock up in the air and seeing how much it like impacts the ice, and then listening to the ice and like standing on the ice a little bit to see if they can get a hold of it. They're a professional. I would tell no one to do that, but it's because she's looking for like the smoothest ice she can find, and that's like when it's very, very new. It doesn't have any like melting on it yet. It's just like clear ice. So from a recreational point of view, that's what she's looking for, right? When you get to the white ice, once like it snowed, like the ice kind of starts to get ruined and you can't ski on it much anymore. Which I think is why sometimes in at least I've heard in like Michigan and places they'll like flood the lake on top of the like pump water onto the top of the ice sheet to get a nice smooth surface again. But yeah, from a recreational point of view, that's challenging. And I've been talking with her to see if we can get like a network of people to start taking those measurements really early on. Because if someone could go out and say like, okay, there's definitely ice here, not only because mountain systems are massively understudied and it's hard to get data on them because they're often it's dangerous to go up into the mountains at that period of time, or it's just labor intensive or cost prohibitive. So if people are going out recreationally and going out and saying, okay, there's definitely ice on this date, and it's this thick, it's 2 centimeters, because like I was saying earlier, most of the data doesn't exist before you can get out onto the ice, right? So all of our ice core measurements are after the ice is already at least 10 centimeters thick, and often we can't get out that fast. So we're seeing after the ice sheet's pretty well developed. But if we could get those shoulder seasons, if that were possible. I don't know if people will really be going out at the end of the season because probably the ice not isn't so great. But at least the early part of the season when it's forming, I'd really like to try to see if I can turn that into a long term study.
Yeah, well, I can tell you at least. So I live in Western Massachusetts, and there's like a Facebook group where people are like, "Here's what the ice conditions are in the area," and usually it's the like where is there snow? It's the white ice sort of thing. But early season, it definitely is like, okay, I just skated here. It was this thick.
Oh,
So I
cool.
think people want to share that information. So yeah, that'd be so cool.
Yeah, thanks.
And because I'm a nerd and I also used to work at NSIDC, David, to your earlier question, I don't know if you saw in the chat, there's some really old lake ice records that are housed at NSIDC as well. But not
Yeah,
to Josh's point, they're not as consistent. They're not about quality, so it's not directly relevant for this for sure.
yeah, but phenology is some of the oldest stuff we have, at least like meteorologically as well. Lake Suwa has been recording ice in Japan for hundreds of years, so it's pretty wild.
Very cool. I'm always fascinated by lake ice because so I live in Manitoba where we're in winter for like 6 months and lake ice fishing is incredibly popular. And similar to Alan's Facebook group about wild skating in Massachusetts, there's a massive Facebook group here about ice fishing. And this time of year, it starts to fill up with pictures of people whose trucks have fallen through the ice because they insist they still need to get out on the ice and catch more fish.
Yeah.
Um, Even though it's, close to zero and above zero nowadays. So.
Yeah, in Georgia Bay, I don't know if you saw like a big chunk of ice just broke away from the shore, and before like all the people who were on it, luckily everybody got rescued, but they had floated out I think something like 11 kilometers before they could get rescued.
And they
So
were all rescued by helicopter, right? They all had to be flown off
helicopter,
the ice.
yeah,
Yeah.
yeah. So it can be very dangerous, and actually we rely on the ice fishing groups as well to get a handle on when we can start to go out.
Yeah.